Welcome to my presentation about McSee, evaluating advanced Rowhammer attacks and defenses via automated DRAM traffic analysis. Before getting started, let me give you a quick primer on DRAM and Rowhammer. So multiple DRAM chips are today typically mounted on DRAM modules, and each chip consists of multiple DRAM banks that are organized into bank groups, and each bank consists of matrices of rows and columns with capacitors holding charge. Rowhammer is a memory disturbance error that occurs if rows are repeatedly accessed. For example, two rows with one row apart is in a double-sided pattern will eventually cause bit flips in the row in between, the victim row. With the DDR5 standard, some changes were introduced. The DIMM is now split into two subchannels. There is a fine granularity refresh mode, sending refreshes to single banks only, but twice as often. And there is a new Rowhammer mitigation feature called refresh management that gives the DRAM device more time to mitigate Rowhammer. Rowhammer can be described as an arms race in the dark. On the one side, we can see more and more sophisticated attacks, such as sledgehammer, hammering multiple banks in parallel to trigger more bit flips and facilitate exploitation, and new disturbance effects, such as Rowpress, that keep rows open for longer. And this raises the question, do these attacks exploit the DRAM device as they intend? On the other side of that race, we have improved defenses. For example, the RFM feature introduced with DDR5 that uses per-bank activation counters. Whenever a certain RFM threshold is reached, the memory controller sends RFM commands to decrease the counter. Given that DDR5 devices are already available since November 2020, it raises the question if they use these optional features at all. To answer these two questions about advanced Rowhammer attacks and DDR5 mitigation features, we built the McSee platform. When designing our platform, we had three goals. We wanted a solution that is suitable for DDR5s in terms of speed, number of channels, and automation. A flexible solution that allows us to look at different DRAM form factors and standards, and a solution that is accessible by relying on hardware that might already be available in universities. Here you can see the McSee platform that allows us to observe the DRAM command address bus traffic on a DRAM command level. It supports up to 18 digital signals and is powered by a custom data processing pipeline. More in detail, our platform consists of a high-speed oscilloscope, a digitizer, an analog probe to synchronize the workload with triggering of the oscilloscope, and soldering leads that are soldered to a custom DDR5 UDIM interposer. To make McSee practically usable, we had to optimize our data processing pipeline by using a different data output format named XMLDIC instead of the baseline, the CSV, writing a custom converter for that format as the vendor's Wave Studio converter was rather slow, upgrading the network card to move files to the processing server faster, and finally parallelizing the conversion and decoding. With these optimizations, we got a 16x speedup, making this platform practically usable. And in fact, optimizing the speed was not the most challenging, but figuring out how to properly decode the DDR5 bus with its particularities such as multi-cycle commands. The McSee DDR5 decoder is platform agnostic, open source, and can be found in our artifacts. Equipped with McSee, we can now take a closer look at multi-bank hammering in sledgehammer and keeping rows longer open as shown in Rowpress. For sledgehammer, we use an Intel Coffee Lake machine and run the code with a fixed number of banks. We do this for 1 up to 16 banks while capturing traces with McSee. We can see that the total activation throughput increases up to 6 banks. Thereafter, the activations per TRFI per bank drastically drop. And as a low activation rate might make it hard to bypass TRR mitigations, we conclude that it is beneficial to hammer up to 6 banks on this machine. We also looked into their hypothesis, suggesting that if more banks are hammered, less activation reordering is happening, as they observed a higher number of bit flips per bank. For this, we looked into the distance between consecutive acts to the same aggressor pairs. And we found that the results follow the expected trend, but we find up to 6.7 times more activation reordering when increasing the number of hammered banks from 1 to 7, which invalidates their hypothesis. To analyze Rowpress, we again used the same coffee lake machine with the same DIMM they used in their original work. As a sanity check, we reproduced the original results and triggered Rowpress bit flips. Then we fixed the number of cache block reads and measured with McSee the average row open time TAC-on, here in blue in the plot. And if we put these values in perspective of the AC min degrees of their work, we can see that the AC min only decreases by 2x rather than 17.6x reported for their most effective Rowpress pattern. And this shows that there is still a lot of potential to improve Rowpress attacks on real systems. For the RFM analysis, we looked into both the RFM data reported by the DIMMs and the behavior of the memory controller. We first had to write a custom DDR5 SPD decoder, as existing tools did not support reading out these values. And we looked at 3 RFM parameters. So if RFM is required by the DIMM, the RAA-IMT, so the rolling accumulated activation initial management threshold, and the RAA-MMT, so the maximum management threshold. We found that the most DDR5 devices report valid RFM values, but only one of the 30 DIMMs in our test pool requires RFM. For our analysis of the memory controller, we considered 3 systems: Intel Alder Lake, Raptor Lake, and AMD Zen 4. We performed double-sided Rowhammer on 2 different DIMMs, where one does not require RFM and the other one does. We did not find RFM commands on any of the Intel and AMD systems, but on the Intel Alder and Raptor Lake, we found that the fine granularity refresh mode is used by default. Also, we found that aggressor adjacent rows are sometimes activated on Intel Raptor Lake, although our test code never accesses them, which suggests that they are employing the PTR aroma mitigation in their memory controller. So we ran another experiment to investigate how likely it is that a row gets refreshed by PTRR. We hammer 2 aggressor rows for 8K activations with CL flush and M fans between hammers, and we repeat this experiment for 512 times. And here you can see how many PTRRs we can see in area of such block of 8K activations. And we can fit this to a binomial distribution, showing that aggressor adjacent rows are refreshed with a probability of 0.091%. This insight immediately raises the question of how long does it take to naively bypass PTRR. And to calculate this, we take the existing paramodel from previous work and calculate how long it would take to achieve a 50% attack success probability. Within 1 week, we can bypass PTRR with 50% probability on devices with a Rowhammer threshold of 18.8K activations. Within 1 day, on devices with a threshold of 16.7K activations, and in 1 hour on devices with a threshold of 13.2K activations. This essentially means that PTR increases the time to succeed with an attack, but does not completely stop Rowhammer. We think that these analyses are just the beginning, and there is so much more possible with McSee. For example, looking at other DRAM protocol features, such as DRFM or PRAC, once devices that employ these are available. Also, an interesting direction could be to improve Rowpress attacks, or to determine how patterns found on an FPGA could be ported to Intel and AMD CPUs. To conclude this presentation, we looked into advanced Rowhammer attacks and showed that hammering up to 6 banks is beneficial, and Rowpress has a limited effect on real systems, revealing the potential for improvement. We showed that RFM commands are not used on Intel Alder Lake, Raptor Lake, and AMD Zen 4 CPUs, but Intel Alder Lake and Raptor Lake use the fine granularity refresh mode by default. We also discovered that Intel Raptor Lake CPUs use PTRR, a memory controller-based mitigation, to make Rowhammer harder on this platform. If you want to know more about my work, please take a look at our paper.